Welcome to the pre-lab discussion for experiments 3 and 4. We're going to be working in teams over 2 weeks to identify an unknown organic liquid and solid from a long list of possibilities. In order to begin the identification process, we're first going to try to identify acidic or basic functional groups that might be present in our unknown molecules. And this video will focus on that particular assessment. So when we think about using solubility tests to identify the functional groups present, let's first consider the functional groups that might be in your molecule. So it's possible to have an alcohol, aldehyde, amine, carboxylic acid, ketone, nitrile, or phenol as part of your molecule. So the list that's provided in the lab manual arranges the various possibilities according to the functional groups present. When we think about why we can use solubility in aqueous solution to learn something about our organic molecule, it's important to note that most organic compounds which have greater than 5 carbons and not a large excess of very polar functional groups are not particularly soluble in water. There is an exception to this when we have small organic molecules, such as this trialcohol shown here. We may start to see solubility in neutral water due to the low molecular weight, low carbon hydrogen content, and high percentage of polar hydrogen bonding functional groups. So if you see solubility in neutral water, you're typically going to be looking for something that's very small, so about less than 5 carbons, and definitely lots of polar functionality. A few of the possible molecules on our list do meet this criteria, but most of them are organic molecules with greater than 5 carbons. So we're going to focus the rest of our discussion on how we can learn something about those particular molecules. Some of the unknowns contain what we call organic acids. These would be molecules which have carboxylic acids or phenols. And we know that these are acidic because they have an oxygen-hydrogen bond that can easily be deprotonated under basic conditions. By contrast, amines are thought of as organic bases because the lone pair on the nitrogen atom can easily pick up a proton under acidic conditions. Of the remaining functional groups, for instance, alcohols, aldehydes, nitriles, ketones, these are thought of as neutral organic molecules. Even as we change the pH of an aqueous solution, we don't tend to see reactivity and we don't tend to see any solubility. So let's go a little more into detail into the chemistry of why we can use solubility in aqueous solutions at different pHs to say something about the presence of these acidic and basic functional groups. For instance, let's revisit the carboxylic acid. The carboxylic acid shown here is benzoic acid, and you'll notice that it has 7 carbons. So we would expect it to be insoluble in aqueous pH 7. However, when we place this compound into a basic environment, as we've seen in lecture, the base, such as sodium hydroxide, can remove the acidic proton, leaving a resonance stabilized carboxylate anion which is quite favorable. And you'll notice now that the anion itself has a charge. Okay. Charged species tend to have better solubility in water-based solutions. So what you might find for this carboxylic acid in the lab is that if you place the acid itself into a test tube with water at pH 7, you'll observe only a solid, meaning very little of the molecule dissolves into solution. It's insoluble. However, as you go to aqueous solutions that have a basic pH greater than 7, you will notice the solid will in fact dissolve. So you're looking for a clear solution in that case. And of course, if you were to maintain this in an aqueous acidic solution, pH less than 7, you no longer have a base to help invoke a charge onto that carboxylic acid, and you expect to see an insoluble mixture as well. So we have insoluble at pH 7. Solubility, because of the charge we've created on the carboxylate anion. And then below pH 7, we return to an insoluble mixture. So you'll have 3 test tubes in the lab with aqueous solution of these different pHs, and you'll be looking to observe the solubility profile of your molecule. If you had, by contrast, an amine, such as the one shown here, again, you'll notice that we have greater than 5 carbons. So we would expect poor solubility in neutral water because the molecule does not have a charge. If we place this molecule into an acidic aqueous solution, we have seen in class that the lone pair on nitrogen can actually take a proton from that acidic solution, forming an ammonium ion. And this, again, is a charged species, so we're going to see better water solubility. And so for amines, in the aqueous acidic solution, we should see the solution clear up and become homogeneous. Whereas in the neutral or basic solution, we would expect the organic compound to remain insoluble. So when we considered our various functional groups, we saw that both the carboxylic acid and the phenol are acidic. So you might be wondering, if I observe solubility when I treat with base, how do I know which one I have? Some of the other analytical techniques we're going to learn about in this lab might help to distinguish those. But there's one additional piece of solubility information we can get that may help us to get a head start on that distinction. And that is to use both a strong base and a weak base solution. So if we return to benzoic acid, our example carboxylic acid, we saw that in the presence of hydroxide, we can expect a very favorable removal of that acidic proton to give us the carboxylate anion as the conjugate base and water as the conjugate acid. You'll notice that we think of this as an equilibrium that favors the product side or goes to the right, because water is a much weaker acid than the acid we started with. By the same token, I can take benzoic acid and treat it with the weaker base, sodium bicarbonate. So the bicarbonate anion is shown here. With bicarbonate, I can still achieve a deprotonation of the carboxylic acid. It is still a favored reaction, although you might notice that carbonic acid, the conjugate acid produced from this reaction, has a lower pKa than the water in the example with the strong base above. And so maybe this reaction starts to become a little less favorable, though it is still product forming. If I look at the phenol shown here has a pKa of about 11. So you'll notice it's not quite as acidic as the carboxylic acid itself. When treated with sodium hydroxide, we see a very favorable removal of the proton. So again, the equilibrium is going to lie towards the products, giving us a phenoxide anion and forming again that conjugate acid water, which is definitely less acidic than the phenol acid I started with. When I have a phenol and I try to deprotonate it with the weaker base, bicarbonate, you will notice that this is not a product favoring reaction because I would form carbonic acid, which is actually a stronger acid than the phenol itself, making it easy for the reaction to return to the starting materials by reprotonation. So the phenoxide anion is not formed preferentially. So if you were to take an additional test tube in your test tube solubility test, if you take an aqueous basic solution of sodium bicarbonate with the carboxylic acid, you'll notice a clear or homogeneous soluble solution. However, with the phenol, you will notice a lack of solubility in the bicarbonate. So if you have a molecule that seems to be soluble in hydroxide, it's a good idea to then check the solubility in bicarbonate and use that to maybe start to build evidence that you either have a carboxylic acid or a phenol preferentially. In some of our subsequent discussions, we'll talk about how we can use some of the spectroscopy we're going to learn in week to confirm this assessment. So that's how we're going to use solubility this week to try to identify our functional groups. When you're using the solubility tests, one thing to be aware of is that if you see solubility in water at pH 7, remember from the first slide that that tends to be an indicator of a small polar molecule. If after trying to dissolve your molecule in pH 7 water and you observe solubility, if you move on to then try to dissolve this molecule in acidic solution and basic solution, it will probably dissolve in all of them because they're all aqueous based. So this may not be very informative about what functional groups might be on this small organic molecule. To help us learn something further, if you have a molecule that is soluble at pH 7, and you suspect that it's small and polar, you can use pH paper to see if the pH of the neutral water has changed upon the dissolution of your compound. So if your compound is a small polar molecule that also has, say, carboxylic acids, you should see the pH of the solution be indicative of an acid being dissolved. If you think you have a small molecule that has an amine on it, you should see your pH indicator indicate that something basic has dissolved in solution, leaving a more basic change in the pH. So this can be very helpful in learning more about the very small polar molecules where we're not going to be able to distinguish the solubility in strong acid versus strong base because it's just going to dissolve in anything that has water. One other thing to consider is that if you run your solubility test and you see no solubility at pH 7, so you have either an immiscible liquid that doesn't dissolve in, or a solid that sits at the bottom at pH 7, and in acidic solutions less than 7, as well as in the basic solutions greater than 7, you can probably conclude that your molecule is greater than 5 carbons and contains our more neutral functional groups, such as the alcohol, aldehyde, ketone, and nitrile. And you might be wondering, well, how do I go about narrowing down the list if I fall in this category of being neutral with so many possible functional groups still remaining as possibilities? And this is where infrared spectroscopy, which is linked in the second pre-lab video, is really going to help you narrow down those neutral possibilities. So once you have more data, you'll be able to visit these long tables in the lab manual, and you'll be able to really start to narrow down from the hundreds of possibilities to much fewer possibilities. And we look forward to working with you this week on this. Have a great week.